So hello everybody. Thank you so much for being here. Today I'm pretty excited to talk to you about some research I've been doing focusing on the history of inland water quality remote sensing. Now when I say inland water quality remote sensing, specifically I'm referring to the estimation of optically active water quality constituents. And these can be chlorophyll A, used as a proxy for total algal biomass, total suspended sediments, either organic or inorganic, color dissolved organic matter, most often used as a proxy for total dissolved organic carbon, overall water clarity, or nutrients which may not be optically active themselves but are highly correlated to one of these previous parameters. And so before I get too deep into this, I want to give you a little background on why we did this project. My colleague Matthew Ross and I wanted to embark on a large-scale remote sensing of inland water quality project, and subsequently we began diving into the literature and pretty quickly found some questions about the feasibility of retrieving water quality parameters at a large scale. And this was both from the published literature as well as from kind of national research directives like the NRC Decadal Survey. We found that as we read the literature, it seemed like inland water quality remote sensing had evolved much more slowly than related fields like terrestrial remote sensing and ocean color remote sensing. For both of these, throughout the 70s and 80s, you kind of had methods development that led to really global scale data products and data analyses by the 80s. Comparatively, inland water quality remote sensing really has no global data products and definitely has no global analyses. And finally, we found that there was a certain novelty in looking at the history of the field. Authors like Matthews and Galizade have done a really great job providing methodological reviews of the field, but no one's gone into it and examined how the research focus of inland water quality remote sensing has changed over time. And so to analyze this, we kind of took a two-pronged approach. We identified broad-scale trends in the literature through a bibliometric analysis of Scopus search engine results. And then we identified a subset of papers and read them in detail and cataloged the study characteristics as well as the focus over time. So just to start here, this is the results of the Scopus search query results, colored by the search term which it was returned by. And you can see a few things right away. The majority of the publications are focused on lakes and rivers, with a smaller subset looking at estuaries and deltas. And also, you can just see that the field has been growing exponentially over the past 50 years. This growth is really only important if we compare it to the growth in academic publishing overall. And Bornman and Mutz in their 2015 paper estimated that for academic publishing, the doubling rate is about 23.7 years. We can calculate the same metric for inland water quality remote sensing, and we find that it's doubling about 3 times as fast. Telling us that really, even compared to publishing as a whole, this field is growing quite quickly. Just quickly, I want to touch base on where these publications are coming from. Featured here are the top 10 journals which returned results from the search query. And there's a couple things I want to point out. First, about 30% of these journals are explicitly remote sensing journals. And about 60% of the publications within these journals are coming from those remote sensing journals. And this tells us two things. It tells us that a large part of this field is remote sensors addressing a remote sensing audience. And it tells us that a lot of these publications that are published in these remote sensing journals are more likely to be methods-based journals rather than papers incorporating remote sensing of inland water quality as a tool to better understand inland water quality dynamics. And so moving on to our detailed index, we identified a subset of 235 papers from our search query, as well as from existing reviews. We read each paper and we cataloged the publication characteristics. These things included the modeled parameters, whether it was chlorophyll, TSS, CDOM, et cetera. The study scale, how large of an area covered, the duration, the modeling approach, most typically it was empirical or semi-analytical. Semi-analytical being a more mechanistic approach. Sensor information, what satellite platform it came from, whether it was hyperspectral or multispectral, the water body type, lake, river, et cetera, and finally model error metrics just to measure how these models have performed over time. Next, we categorize each publication based on the level of analysis. In order to reduce the subjectivity here, we really focused on 3 key metrics: whether there was an explicitly proposed hypothesis or science question, whether there was either spatial or temporal analysis, and finally, if the majority of the figures within the publication focused on methods and validation or focused on the impacts and drivers of water quality. Subsequently, each paper was categorized as either a methods paper with some slight pattern application, pattern or trend analysis paper, or a water quality science paper that's really using remote sensing as a tool to further our understanding of inland water quality. Before I move too much more into that, I want to touch base on these publication characteristics a little bit more. And here it's a little washed out, but you can see with the figure on the farthest left, looking at modeling approach, empirical modeling really dominated the field for about 30 years, and to a lesser extent, semi-analytical modeling. It's not until kind of the mid-2000s that we see an emergence of machine learning approaches, mixed modeling approaches, and kind of pre-produced satellite products. If we look at coverage scale, here the light blue represents small studies, basically focused on an individual water body or small region. And as you move towards darker red, you're moving up to kind of the watershed scale, the state scale, and even the country scale in some studies. Similarly, for study duration, the light blue represents very short studies, snapshots. And as you move towards darker red, you're moving towards 5, 10, 15 years. And if you just calculate the correlation coefficient between publication year, coverage scale, and coverage duration, and study duration, you find that all 3 of these parameters are significantly correlated at 99% confidence. What this tells us is that over time, researchers have been using novel modeling approaches to increase the spatiotemporal domains of their studies. We only care about these spatiotemporal domains if these models are still performing well. And here you can just see the trend in reported R-squared metrics over time. And there's a couple things I want to point out. First, we've been able to do this pretty robustly for a long time, right? Even dating back to the early 80s and 70s, we have pretty high reported R-squared metrics. And as you move through time with increasing complexity in your spatiotemporal domains, we maintain a pretty high level of fit. So next, I just want to talk about these publications based on their level of analysis a little bit more. We can look at level of analysis in a similar way that we look at study characteristics, both spatially and temporally. And here, the kind of greens and yellows represent higher levels of analysis, either really spatiotemporal trend and pattern analysis, or kind of water quality science papers that are really leveraging remote sensing in new and novel ways. And you can see similarly, starting kind of in the mid-2000s, we see a large increase in the number of publications using remote sensing as an effective tool. Before 2008, only about 7% of publications fell into this highest level of analysis. Post 2008, we have almost 30% of publications falling into this highest level of analysis. Spatially, there's a couple interesting things to point out. You can see some very high level of analysis papers up in high latitude regions in Arctic and boreal areas. You can see a large cluster of them kind of in the Yangtze Basin in China. And finally, you see a few of them kind of in the developing country where in situ monitoring may not be super prevalent. So to give you an idea of what I mean when I say high level of analysis, I kind of want to highlight a couple papers that stood out. Kin et al. In their 2015 paper used a dynamic forecasting model to predict harmful algal blooms in an important drinking water reservoir in China. Ultimately, their model resulted in a doubling of the amount of harmful algal scum that was removed from the reservoir. Overeem and others in their 2017 paper used Landsat-derived suspended sediment values to measure sediment export from the Greenland ice sheet. They found that while Greenland only accounts for about 1% of freshwater exports to global oceans, it accounts for about 8% of sediment. Torbeck and others in the 2014 paper incorporated Landsat-derived water quality parameters into an eco-epidemiological model looking at ALS hotspots, and found that proximity to degraded water quality significantly increased the likelihood of being located within an ALS hotspot. And finally, Falsini and others used MODIS imagery of a 2011 flood on the Mississippi and found that management decisions made during the flood increased sediment export along the main side of the Mississippi, but actually increased sedimentation rates in neighboring Atchafalaya Bay. And so what are the resources that have allowed us to kind of push this level of analysis to a new level and use remote sensing as a tool to better our understanding? First, there's been a dramatic increase in access to data. This is both satellite Earth observation data as well as in situ data that we can use to calibrate and validate our models. And here I would just put a plug in for my colleague Matthew Ross, who's presenting a new database this afternoon called Aquasat that combines these Earth observation data and field data into one comprehensive data set. We have improved pre-processing and modeling techniques, and this is specifically addressing things like atmospheric corrections that have historically been super challenging for inland water quality remote sensing. We have improved software and computing power. This both goes for our local machines as well as platforms like Google Earth Engine that basically provide cloud computing to individual researchers. And finally, we have national research directives that lead directly to increased funding for the field. In Europe, we have the EU Water Framework Directive, and here in the US, we have the NRC Decadal Survey. So moving forward, these resources are going to allow us to better understand carbon cycling in lakes and reservoirs, better predict and monitor harmful algal blooms in really important drinking water reservoirs around the world, monitor water quality in remote and sensitive ecosystems that are changing quickly with climate change, specifically Arctic and boreal areas, and finally, just better monitor our anthropogenic impacts on freshwater systems as a whole. And so with that, I will gladly take any questions you might have. Thank you.
Simon, I have a question for you. So what's the low-hanging fruit in your mind? What are we good at right now in terms of water quality parameters, and what are the really hard ones, and why are they hard?
So the low-hanging fruit is definitely a simpler parameter like water clarity, right? You basically have kind of returns in the red range that pretty accurately capture it. It gets much more difficult when you're talking about trying to model like dissolved organic carbon, because our best proxy for that is color dissolved organic matter. And the ratio between those two things is not necessarily consistent over water bodies. Plus you have kind of low level of returns already over a lot of water bodies. And so for something like CDOM that's really absorptive and lower wavelengths, that signal can kind of get clouded out pretty easily.
Can you give us an idea of the future opportunities for high-resolution hyperspectral in space? Where are we at, and what can we expect in the next 10 years?
Totally. So there have been a lot of airborne sensors that have been utilizing hyperspectral imagery. Specifically, a lot of that work is focused on chlorophyll because you have these fairly narrow absorption and backscattering peaks within the spectral signatures. And I think that, yeah, I think it will significantly improve our data products and allow us to create generalizable models across regions, in part because I think we'll be able to produce better atmospheric corrections with hyperspectral imagery, which is one of the key variables that stops us from applying a certain model across a wide range of situations.
Thank you. Our next speaker is going to be talking about satellite-based precipitation estimation, and it's Robert Adler.
Good morning. I'm going to run through some examples of telling you where we are with satellite precipitation and information in terms of hydrology. I'm going to go fairly quickly. I think most of you are familiar with the main methods of doing satellite precipitation estimation, including visible infrared, which gives you the possibility of using geostationary data, high time resolution, but there are very indirect relations. Passive microwave, mainly from low orbit or from low orbit. Here are some of the instruments. And they give you a better connection to the rain and the physics of the radio transfer, but they do have limitations, for example, shallow rain over land. And then you have radar, and that's a limited number of satellites that have radar. including a low orbit, the Global Precipitation Measurement Mission, and earlier the TRIM mission, CloudSat at 90 gigahertz, very good at high latitudes. And today we actually have sort of a golden era of analyses because we have the ability to combine passive microwave, visible IR, with the accuracy of the radar and the passive microwave, providing a best estimate to kind of link these things together. And there are a number of applications that we obviously use this data for, and one of them is very large-scale hydrology, even on a global scale. And one of the main products is one I'm associated with, the Global Precipitation Climatology Project, which focuses on giving monthly estimates of precipitation globally complete. And for example, and we do this even quasi-real time, so this is last month, just finished up a few days ago. You can get a map, a globally complete map of precipitation. It uses passive microwave and IR and other things over oceans, gauges and satellite over land. You can look at the anomaly, and we have what we think is maybe the start of the 2019 El Nino event. And so you're able to look at this and compare it with the research product that goes back to 1979. And that's important because then you can do composites of things like ENSO anomalies, which are very important, obviously, and the most dramatic anomaly. This is actually El Nino minus La Nina months, so it's a El Nino type of pattern. You can see the large positive anomaly over the central and eastern Pacific Ocean, negative anomalies other places, and you can easily see how what's happening over the ocean is connected to what happens over land also. In fact, you can see the positive anomaly here going from the eastern Pacific across the southern US, and lots of other features, even extending into very high latitudes. This is an important phenomena, and we're able to document it and look at these linkages. We've heard about water cycle earlier today, and this is one from a paper in 2015 that uses a lot of satellite data. And it's got the usual things, the evaporation from land and ocean, precipitation over ocean, precipitation over land, runoff, et cetera, and tried to do a balance with the latest data over about the last 10 years. The GPCP land value is here, and actually the white data is the original data information, and then it's adjusted to try to reach a balance. It has to be adjusted only slightly. Same thing over ocean. So we have a pretty good handle on ocean and land gross precipitation in terms of means, in terms of climatologies. But obviously we're interested in changes, including the interannual changes I showed you before. But one of the things we're also interested in this large scale is trends. This is the trend from GPCP, with the blue being the positive trends. And then you can go and compare that with climate model results over about roughly the same period, including an ensemble of AMIPs here and a CMIP run here. And if you look or maybe squint, you can see some similarities. This feature here, the blue feature, is corresponding to that, the Indian Ocean. You can see a relationship here, and you can get an idea, but it also gives you a handle that if you're gonna accept the observations, that you better use the climate model trend information carefully. Interestingly, the CMIP is actually on a different scale. It has a weaker response. So there's all kinds of information. So this building up of this satellite climatology information is very important. It even comes through in intensity changes. This is in the tropics, land and ocean combined. This is the mean rain rate, and the black is the observed from GPCP analysis, and that shows an increase, and so do the models. Then you can go up to the 95th percentile, the very intense rain, on a monthly scale. We're talking about monthly 2.5 degrees, and you can see an increase both in the observations and the model results, which is very interesting. And intermediate percentiles are decreasing. So we're really using the satellite precipitation, getting a good handle on this. But we also want to look at much higher or finer time and space resolutions. And we're getting to that with things like the iMerge product from NASA. This is the GPM product. And there are other products like this that are really using merged passive microwave, even infrared observations. And using this, the radar information, for example, from the TRIM previously and the GPM core satellite, to look at this and do this analysis. So you can get down to 3 hours or even finer, and about 25 kilometers or even a little bit finer spatial resolution. And that gets very interesting to start now looking at daily precipitation, although we only have about 15 years of this data. So now not only there you can get the mean precipitation, but you can look at what the 95th percentile of the daily precipitation is based on the satellite, both from over ocean and over land, and make comparisons, do things like that. But you can also use that 3 hour or even finer time resolution to go into hydrologic modeling. And this is an example from our global flood monitoring system, which we run in real time, quasi-real time, about 6 hours after real time. The rainfall data goes into a land surface model. We calculate runoff. We do routing. This system has really been put together by my colleague Huan Wu. And then by comparing these real-time runs with a retrospective run over the last 15 years, we can look for set thresholds at every grid point for flooding. And, oops, I think I went too fast. There, it shifted. And you can get an idea where there's flooding. You can look at stream flow calculations, essentially at any point on the globe, 50 north to 50 south. And then you can, in this case over Peru, look at heavy rain events. You can see where we're estimating the flooding. You can get, in this case, at one city along here, you can get the stream flow as a function of time. You have your flood threshold, so you get an idea of where you are related to that. You can make an estimate, again, almost any place on the surface of the earth. And by using NWP rainfall, you can even make forecasts of that to add on to your estimates based on the satellite data. And by using 1 kilometer routing, you can come up with inundation mapping across the globe. This is an example from in that Peru case. And this allows us to get to the point of even comparing with other satellite data, like from synthetic aperture radar, which is estimating inundation. And here's a case a few months ago on the east coast of the United States. This is Hurricane Florence. This is the actual rain gauge-based radar rain map from that area. And this is the satellite estimate here, and you can look at this. But the key thing is we did a pretty good job from the satellite estimates, up to about 200 millimeters for a total for the 7 days. But when you got to the peak numbers, the iMerge estimate was about 500 millimeters. The gauges were coming up to 700 millimeters. This was obviously a very heavy rain event. But then we can look, oops, I think I skipped one there too. This is on one day what we were getting in terms of where we were seeing the flooding. This is from using the satellite rainfall. And then you can compare that with obviously high flow conditions from the stream gauges here in North Carolina. But things are not all that well. There are differences. This plot here with the blue is the USGS stream flow for this is for the Neuse River upstream of New Bern, North Carolina. And here's, I just plotted our estimates from our 1 kilometer run from our estimate based on the satellite precipitation data. So we were early, we got to a higher peak, we came down, but there are some things going on the ground where they were trying to control the stream flow, obviously via the dams, and our global system does not include any dam information at the moment. So there are limitations like that also. And we can even do inundation mapping over here, and then we can compare it with what's actually happening on the ground to get a better idea how we're doing. Another application that's related to related to hydrology is landslides. And this is work by my colleague Dalia Kirschbaum at NASA Goddard. And with landslides, the where of the problem is what areas are susceptible to landslides. And this is a map of that with the yellows being the main susceptible areas. And that's related obviously to the slope, to the soils, to the vegetation, et cetera. So you can come up with a susceptibility index. And then the when of the problem is related to precipitation again. So what they've done in this case is use that same type of data I was using or showing with the floods to do landslides, and they use an antecedent rainfall index, obviously looking at the past few days of rainfall, estimating, and then comparing that with the susceptibility index and coming up with where they would think that there was a higher probability of landslides occurring, and doing this in quasi-real time again. And this is an example. The background that's very light is actually the precipitation, and I'm showing on 2 days is actually from a movie loop. The actual where they're estimating where they're landslides, with they have sort of two levels of that, the moderate hazard and the high hazard. And they give an indication here, and you can get an idea of where these landslides are going to occur. It's really showing more of a potential than an exact happening, but it gives you an idea. And one of the nice things about this is then you can go and look quasi-globally and get an estimate of how frequent landslides are occurring, at least according to your little algorithm or model. And you get maps like this. This is essentially a climatology over a few years for July. And as you would expect, you find the higher frequency of landslide or estimated landslides coming in the mountainous areas, but it gives you an idea. And not only can you do this kind of thing, but you can also do look at variations. And for example, in two different regions here in Peru and over Taiwan, you can, the curves here are showing from the algorithm the seasonal cycle of landslide estimation, and the bars are showing landslide reports. So you can start comparing landslide reports with estimates you're making with your algorithm, and you can study seasonal cycle, interannual cycle. You can study the effect of ENSO on landslides, et cetera. So it's very interesting. And I'll just summarize by saying that I think satellite rainfall information has added significantly to the calculation of a number of hydrology-related applications. And even on the large scale I was talking about at the beginning, understanding the ocean-land relationships, et cetera. But we still need to do more. And advancements in this kind of activity are going to require finer resolution and more consistent and accurate precipitation estimation. Even though we can make these calculations now, they're obviously based, their quality is based on how good the precipitation is, in addition to the quality of the models used. And I'll stop there. Thank you.
We have time for a question.
Can you speak just a little bit about the density of rain gauges on the ground that you feel to be optimal complementarity to the emerging satellite measurement?
Well, I think we're never going to get the density of rain gauges on the ground that we need to do it everywhere. But we do need to have areas where we have strong validation activities so we can really judge how well we're doing. The satellite estimation of precipitation over land is difficult. And there are physical limitations. The radars, which you would really like, are obviously infrequent. So we need to parse these together to really come up with the best estimate.
Thank you.
Next, we're going to have, you're good, William Custis talking about thermal remote sensing for evapotranspiration estimates.
Okay, thank you. So what I'm going to be talking about today began from an article that appeared as part of the Fife first Isleskip field experiment special issue that came out around 1992. I would like to also qualify that, thermal remote sensing has a history prior to that involving a lot of agricultural applications, including the crop water stress index that was developed by Ray Jackson back in the 70s. And even before that, when there wasn't actual radiometers that were sensing the temperature, there were leaf temperatures being made on thermocouples that biologists were very interested how the temperature of the plants were responding to water stress and other factors. I'd also point out John Norman, an emeritus professor at University of Wisconsin, was one of the main founders of this approach. I think has some real utility in providing evapotranspiration using thermal remote sensing. Martha Anderson and Christopher Hain have been key players in moving this land surface modeling approach forward to the regional and continental scales. So the paper I'm talking about was a summary article that was in this special issue. And, a focus of the Fife experiment, which were in 1987 and 1989, were to look at ways of using satellite remote sensing for estimating surface energy balance and land surface exchange. One of the conclusions in that article was an analysis done with radiometric temperatures observations from a helicopter that was flowing during a number of the intensive observation periods or field campaigns during this experiment. And what they did was they ran a basic single source model using radiometric temperature to estimate sensible heat flux, which is on the right-hand side there, and compared it to eddy covariance tower measurements. And you can see there's quite a bit of scatter. The other thing they did was look at an aerodynamic temperature derived from the eddy covariance measurements compared to the radiometric temperature. And a key conclusion from this analysis was, as you read down there, unfortunately from our research, we also found that remote estimation of surface temperature to useful accuracies is problematical. Consequently, the use of thermal infrared measurements to infer sensible heat flux is probably not feasible to acceptable accuracies. Well, this result led to a group that felt thermal remote sensing had significant value, hold a workshop in France in 1993, so following this work, and to more in detail explore what was going on with trying to use thermal remote sensing in energy balance work. Sort of the traditional ways of using thermal remote sensing involved this KB parameter that looked at the difference or the efficiency of momentum versus heat transport from the surface. And one of the conclusions in looking at analyses that people have done with the data is that the present empirical approach must be reassessed and a more rigorous analytical approach developed for complex surfaces with partial vegetation. So the current theory and approaches that were derived from laboratory experiments and some field studies, which are these two curves that were summarized in Broussard's Evaporation book, compared to actual observation using thermal infrared data, show considerable scatter and uncertainty. And this was one of the cruxes of the problem, was that trying to use this type of approach seemed to have real difficulty in complex landscapes. So, and as a result, we would end up with quite a bit of scatter when we compared these types of models with observations. These are notes from John Norman that were actually written during the workshop after some discussion about what are some of the impediments that doesn't allow us to get a better result with thermal remote sensing. And what you see here is the realization that you have transport from the soil substrate surface and from the canopy that are going to be at different efficiencies, and in this case they're related to the resistances. And this is of primary importance when you're trying to interpret the thermal emission from the surface, because it's not only related to the radiation partitioning that goes on, but also the convective transport that goes on. So not considering those effects can really have an impact on a model result. And he sketched out some ideas about how we would do the partitioning between the soil and canopy based on radiation and energy transport theory. And so from that came also from that workshop came a publication that was in Ag and Forest Meteorology called Thermal Remote Sensing of the Energy and Water Balance over Vegetation. And in that set of articles was a paper that was senior authored by John Norman on this idea of using a source approach for radiometric temperature and energy balance estimation. So what's now called a two-source energy balance model is really a system that partitions the radiation here for the soil and canopy elements and distributes that in terms of sensible latent heat flux and soil heat flux for the soil, and then the canopy sensible and latent heat flux. The approximation here made is that this radiometric temperature is composed of these two components, the soil substrate and the canopy, based on the fourth power law for radiation. And this temperature is constrained with these energy balance components. A part of the model that gets an iterative solution is using some parameterization of the latent heat flux or the transpiration from the canopy. Several different approaches are being currently tested and evaluated. The simplest being the Priestley-Taylor approach, but then the Penman-Monteith and light use efficiency approaches are also being developed and tested. So the idea is here that with this sort of radiometric temperature partition between the soil and canopy, it treats explicitly the coupling that goes on differently between those two sources. With some simple geometry, you can accommodate off-angle observations that are influenced, say, by more of the canopy than soil, depending on view angle of that sensor. And it provides information on the flux contributions from both the soil and plant elements, which can be quite useful. So, in essence, an example that going from some of these original approaches that tried to treat it as a single source element in these complex type surfaces where you have soil and vegetation interacting to more of a two-source system, you see an improvement in the predictive capability of the model. So since that point in time, so we've been trying to evaluate the model over a variety of landscapes, including even snow-covered area where we've recently developed a snow-based two-source model, to traditional agricultural crops, to rice, to open savanna with trees, so very kind of complex and diverse cover to very organized cover conditions. And so the point is we're really trying to evaluate and refine the model based on various land cover types to see how well it performs. And if refinements are needed, they're made part of the whole modeling approach. So the real advancement beyond the field scale came with a development through Martha Anderson's work of a regional model that uses GOES data for a time rate of change of temperature coupled to the boundary layer. What this did was two things. It provided a way of modeling the actual air temperature that's computing the flux over the land surface, as well as a time rate of change of temperature, which removes some of the issues with calibration of an absolute radiometric surface temperature, which has some uncertainty. Couple that to a disalexy or disaggregation technique, the atmosphere-land exchange inverse model. It can take the radiometric temperature offered by satellites with finer resolutions, disaggregate those fluxes to smaller scales where we start looking at land use, land cover changes. And these are coupled together to give constraints on the energy balance from the larger scale system to give us reasonable results. So we have a multi-scaled system now that can go from global continental scales to the scales of where we're looking at individual fields, which is important in agriculture. This whole process, though, needs to, and has recently been developed, a data fusion technique that merges the hourly data you get from geostationary to daily information and biweekly information you might get from Landsat to try to produce something on a continuous basis, a daily basis, at finer resolutions. And that's what's being worked on now. There's still some skeptics out there who believe this radiometric temperature is not useful. The problem is they're not using the right approach. They continue to try to solve the equation using a simplified radiometric temperature with a single aerodynamic resistance. And so their conclusion is that they're not able to produce a reliable flux using some integrated temperature or a simplified model. So now we've been able to apply this, like I said, at larger scales over different landscapes, and testing how this works at sort of the watershed scale and evaluating with eddy covariance towers and water balance models. Some of the useful information that can be obtained when compared to, say, water balance models or land surface models, for example, here, is signifying the differences we see with the regional model in terms of ET differences that are really the result of irrigation. Some of these water balance models don't have the kind of information that provides where there is irrigation going on, and the Alexi model provides that. There's also areas where due to water table depth, you get a continuous water use that again can be picked up by the thermal signal and not seen by sort of land surface models. Also, Martha Anderson has utilized the ET model along with this development of evaporative stress index, which relates to actual to potential ET, and it's been shown to predict flash droughts. The flash drought of 2012 was really picked up by the SC model before some of the other types of drought models could indicate the effect of flash drought. So that obviously has an effect on yield. So this type of modeling system is very useful for looking at the effect of agricultural drought on yield. So with this multi-scale drought system, we can get down to the field scale, which is very important for agriculture, but also in natural environments where you have ephemeral streams and you have these riparian zones that you're not going to see at the MODIS resolution. You really need the Landsat resolution to pick up those ephemeral channels or these riparian zones. And lastly, there's being work done on looking at the effect of agricultural practices in arid regions. Here you see the depletion being seen by the GRACE satellite at a much coarser resolution. But it's this multi-scale mapping where we can get down to the Landsat resolution where we really see the agricultural applications that is causing the effect of the groundwater depletion rates. So land surface temperature has come full circle to a point where we feel it can monitor changes in water use. It can improve hydrologic monitoring for flood and drought predictions. It has improved accounting for current water use and crop water productivity. And it has a means of detecting crop stress and perhaps can be used in yield estimation. So what we can manage, we need to have to measure. And so this is, I think, a useful tool in the toolbox of trying to get at evapotranspiration. Thank you.
One question?
Is it possible to also assess groundwater consumption with these methods?
Well, yeah, presumably if you had a water, you had a water budget accounting over time and you knew that they were getting most of their water from the groundwater. I assume then you could do some sort of a budgeting to realize what's being drawn down from the groundwater.
Thank you. Our next speaker is John Selker, Thinking Across Scales in the Vadose Zone.
Thanks very much, everyone, for coming. I want to first tip my hat to Jim Douge, who really, I think, kind of presented back in the 70s and 80s this notion of how water across different scales takes on fundamentally different characteristics, and how we really have to be very cautious at extrapolating from one scale to the next. And so I strongly encourage you to look at Jim's work, which I think was seminal. And we also have a video of Jim, if you want to see it, where he gives this talk at Oregon State. I appreciate being invited here. I am, to one significant digit, 100 years old, and so I do think I am an appropriate speaker to this conference. Jim did, I can't get this in advance. What's the advance trick here? Hold the white keyboard. Oh, it's two keyboards. Jim did give that talk under one condition. He said, I'll give it as long as I'm still alive next year. And he was, thankfully. Unfortunately, we lost him since, but a wonderful, wonderful mind. So I'm going to give you the conclusions first. So first off, we can do wonderful predictive soil physics at the kind of up to 2 meter scale. That's a classical Richards equation sort of approaches. But beyond 10 meters, I claim that we have to use a new way of thinking. We have to kind of let go of the techniques and mindset following Jim's advice. And when we go to the larger scales, have to think in completely different ways. And so when you are doing larger scales, you have to be extremely careful at applying Richards equation in those contexts. One-dimensional vertical at 10 meter scale, okay, cool. But don't talk to me about three-dimensional lateral at those scales unless you're really doing your homework carefully. And what we finally will see is that there's some really cool problems out there that the kind of under 100-year-olds need to get on. And so one of the cool things is that the Richardson equation, which is just conservation of mass and Darcy's law, does allow us to explore really cool processes at the appropriate scales. Here I'm showing some of the work of Mark Rockhold and Rocky Yarwood, where they put in microbes and showed in time how the system desaturated as the microbes reduced the surface tension of the water. And also increase the water holding retention in other areas where they put in cells. So we saw that we can take these basic equations, make them dynamic in the soil properties, and make incredibly cool predictions between the experimental and modeled results, and get really good predictions in very complex systems. Similarly, the fingered flow domain is still being a very productive because we can trust the Richardson the equations, and so we can evaluate if we have captured the right phenomena. And so in that hypothesis testing framework, we can actually lean on it heavily and get some very, very key insights. So I think at the 1 meter scale, it's a very, very remarkable, powerful approach. Now let's look at capillary barriers. And capillary barriers back in the late 80s were motivated by basically Yucca Mountain. Yucca Mountain was this big layer cake, and people recognized that the capillarity between those layers would give lateral diversions at the kind of mass scale, which should lead to no water percolating through our waste. What a great thing. And so a lot of us kind of jumped in and said, this is really exciting, this is really cool physics. And so we built these chambers at the 2 meter scale, we put on dye, we had a coarse layer here, the water flows off, wonderful. And we then derived solutions for parabolic capillary barriers that optimize the ability to divert. And so we could actually get optimal behaviors, and we could start designing them in an engineering context. But when we went to the larger scale and started thinking a little bit, we actually saw that at the 10 meter scale, and it's off the scale here, this is 10 meters long, what we see is that micro defects all of a sudden start jumping in and start, the capillarity, which is it's kind of 10 centimeter-ish length scale, kills you when you have anything that has an irregularity at that same length scale. So when you get beyond the couple meters, you start to see that actual reality of limitations of capillarity start to strongly impact the efficacy of capillary barriers. That said, Martin Schroth, who's here today and is someone you should talk to about this, And I looked at this question about can we look at capillary barriers and their impact with respect to non-aqueous phase liquids. Again, a great place to apply Richardson-Richards equation, conservation of mass, Darcy's law, multi-phase, fine. And what you see is that you can actually, this is work from Canada, where they showed that in layered systems, the flow of the non-aqueous phase liquids was strongly impacted by these layers. And then we could say, yeah, here's what happens when there's no water flow and it's just non-aqueous phase liquids. It gives long-range lateral diversion. Interestingly, when there is water flow, and that's why it looks kind of hazy here, there's lots of water coming down, it's wetter, and now the napples actually penetrate the capillary barrier. The water is now occupying the small pores, the napples are relegated to the large pores, and they come dumping right through, leading to isolated patches of napple in the unsaturated zone that will be essentially permanent, because there's no water flow there. So once again, we see the tremendous power at the small scales in terms of making predictions and understanding these critical processes. Also, looking at the Hanford site, where we have highly layered systems, what we saw was that the 10 molar sodium nitrate solutions that came out of the tanks, what it did is it gave lateral, the first absolutely horizontal driven flow due to vapor deposition. So the vapor would actually be drawn out of the material above and below this high salinity material, deposit, condense in it, and then drive the flow. And on the 50-year time scale, these go on the order of 50 to 100 meters. And so when we tried to understand how the waste from the tanks was getting long lateral distances, again, the small-scale processes were adequate to describe these lateral flow processes, which tended to challenge the Richardson-Richards kind of framework. However, the Missoula floods that gave rise to these were very large-scale lateral processes. So again, a kind of a on-the-edge sort of scale. However, when we came back and actually started to apply our ideas to the Yucca Mountain, and this is Laurie Flint's thesis for the most part, what we saw is that the layer cake didn't work at all. And the problem is, take your nice layer cake from a wedding and drop it. And what happens, we know, of course, is that it fragments. It breaks into little chunks, which might be convenient for serving. But from a capillary point of view, the wedding cake is no longer intact. And what we know is that capillary processes cannot jump gaps. And so what happens is the layer cake that was supposed to give us long-range diversion actually delivered water to the crack where it intensified vertical percolation. And this is why, in my opinion, there's a lot of opinions out there. This is why, in my opinion, we have delivery to great depth on the 50-year timescale of the Yucca Mountain. And so the layer cake that was supposed to help us, because people were visualizing it at the inappropriate scale, when you started looking at the appropriate scale and thinking about the process at that scale, then we recognized that actually we had been going beyond the range of applicability. Now let's take a little detour to an area that's, I think, really interesting and has been thought about quite a bit, and that is evaporation length scales. And so in particular, there's been a lot of interest in China right now about what can we do with desert areas, and can we count on water delivery from depth to provide water for plant coverage. And again, our starting place ought to be to think about the appropriate length scale. So looking at the work of Danny Orr and Peter Lehmann and Shlomo Neumann, Shmuel Auslin, excuse me, we see that these length scales, capillary length scales, are all been found to be limited to on the order of 10 to the 0 to 10 to the first meters. So what we see then is this is just an intrinsic piece of observation that has really been recognized now on the order of 50 years. And indeed, looking at the follow-on work that Shmuel and company developed, once again, they're identifying that at 0.2 bars, basically that's the fundamental capillary length scale, 0.2 bars being about 2 meters of head and 2 meters of extent. So again, I want to really reinforce that capillarity is really limited. It just doesn't do long-range work. Okay, so now let's take a look at what if we have a long-range problem. So let's envision a water table that's, say, a couple hundred meters down. Maybe 100 meters would be enough, but let's say a couple hundred meters below a desert. Now at the surface, and so we will assume that this water was put glacially, during an ice age, we had some infiltration, and now we're going to take very dry conditions. And so what we have here is a geothermal gradient, because we're now looking at the larger scale. And so we have to consider the large-scale processes. So we have a geothermal gradient. And what that means is that this is wet soil. It starts off wet. And that means that the water vapor is saturated. And what that gives us then is a gradient in water vapor content, because the higher temperature at greater depth has a much higher humidity. And so what this leads to is that this gradient, what we know, as Fick's law tells us, that means there's a flux. So there's an upward flux of water vapor. The problem is that the upward flux is large here and low there. What does that mean? It means there's condensation. So as the water vapor flux is coming up, it is all condensing out. Almost all of it condenses, leading to this entire domain having downward net water flux, which is quite a cool thing. I mean, we actually went to the desert thinking that the water would be coming up from the water table, but in fact, the water is going down in most of the domain. Now, what's actually happening is that there's this depletion. As we dry, we have a vapor flux zone where we're actually consuming the water in the interface zone. So there's this little interface zone where the water is actually being consumed by the advancing drying front. Now, the cool thing is that this is all quite tractable for a simple first-order differential equation. And so we simply do the mass balance of this system, putting in the vapor flux in the dry zone, putting in the vapor flux and the water flow in the damp zone, and it gives you a first-order differential equation which has an exact solution, which is crazy. How many times do we get that opportunity? And so it has this Lambert function, which at first I thought was really a bummer. But the Lambert function has this totally trivial inversion, which gives us an explicit relationship between time and depth of that drying front, which also then gives us the exact relationship for the flux of water off the surface, which is really handy. So let's take a look at that. And what we see is that the prediction is for time, and this is the depth of the dry interface. And we see as it starts off, of course, at millimeters, centimeters, meters. And this then, how long does it take? Well, it takes about 10 years to go 1 meter. It takes on the order of, to go 10 meters, it takes on the order of 100 years. To go 100 meters, it takes on the order of 1,000,000 years. Okay, so now let's think about this then. So this drying front, to get down to 100 meters, took 1,000,000 years. Now, is this a number that's sensible? Well, it is a number. In that sense, it's sensible. However, that does not mean that it has any relationship to processes on Earth, because what we have are these glacial periods where things get warm and cold that are on the order of 50 to 100,000 years. So this is completely wiped out. And so looking at a more typical glacial timescale, we do get a depth of about 25 meters as the expected maximum penetration depth of the drying front. What happens below that, of course, is we have vapor deposition, and so there's actually a unit gradient of vertical of downward flow. So the drying area is in the top kind of 20 meters or so. There's a little transition zone, and then it's downward flow. So when you look at the salt signature, for example, in the arid areas, keep in mind that there is a net vertical downward flow in those areas. So it's rather kind of fun stuff. This is under revision. That means it's sitting on my desk right now. But anyway, it should be published soon. So again, then coming to the conclusions, prediction in soil physics, I think, is fabulous at the kind of centimeter to single-digit meter scales. Beyond 10-meter scales, that's really where we have a lot of uncharted territory, where processes such as heterogeneity and geothermal gradients become extremely important, and that gives us all sorts of opportunities to rethink. And so I want to push you to go back to Jim Doudge's work and recognize what he said, and that is that we were not going to predict turbulence from the molecular scale water molecule. We were not going to predict atmospheric processes from the simple capillary tube flow problems. And yet water is the fundamental player in all of these contexts. And so we have to be very careful in taking the physics that works at one scale and extrapolating to new scales. But our opportunity, I think, lies here. Thank you very much. So he's asked me the question that should be the basis of an entire session. What toys should we use? And actually, of course, some of you will know that we've been working hard on fiber optics. And so now we can actually, using fiber optics, we can get the kilometer scale measurements of soil moisture and water flux. And so this is work that Shadi Sadeh, Shadi, are you here? Yes, back in the back, that he's led up some fabulous new techniques that allow us to measure at new length scale. So think about this. We can get soil moisture at the 12 centimeter length scale on 10 kilometer transects. And we get this dynamically in time. And so this is where we can actually start to do some of this large scale work. And I think that the opportunity is not only with fiber optics, but many other new sensing and wireless communication technologies really are going to open up this domain tremendously. And we should all be looking that direction, yeah.
Next, we're going to have Andrew Binley talking about hydrogeophysics.
Good lead-in for you from John.
Yeah, he's a tough act to follow, right? So, okay, thank you, and thanks to the conveners for the opportunity here. I'm going to try and give an overview of hydrogeophysics, how it's kind of evolved, and where we're going with this. I've got some contributions from authors here, and I'm probably not going to do their contributions justice, so I apologize ahead of time on that. It's a centenary session. I put this in for André Reville to keep him happy, but he's not here, which is a bit of a shame. But 100 years ago, Schlumberger put forward a electrical prospecting method, and kind of interestingly, we still use a lot of these principles in our geoelectric surveys in hydrogeophysics today. But how things moved on? Well, for some time, geophysics was used quite widely in hydrogeological studies, looking at structures within aquifers. But it probably wasn't until the late 80s, early 90s, that following on from work in stochastic hydrology, that there was a lot of interest in trying to get quantitative information from geophysics. And I got an example up here from Rayfelt in 1992. And even though, and in this study, basically they're trying to look at whether correlation length scales from geophysical measurements, so here streaming potential and resistivity, are similar to those from slug tests and so on, even though the results were pretty inconclusive about the geophysics, and I think that was a result of the immaturity of some of the techniques in that time. It did kind of like set the scene really for where we might go with geophysics and generate a lot of interest. It certainly generated a lot of interest in me in thinking about how we can actually use geophysics to get some spatial information, maybe not to replace things like permeability. I've got to acknowledge here work that Susan Hubbard and Joram Rubin initiated. That we got 11 people to go to Czech Republic, or Susan got 11 people to go, got a whole host of people to go for 11 days in the Czech Republic in a little village to look at to work on a NATO Advanced Study Institute in hydrogeophysics. And this really transformed the field. And the thing I want to highlight here is it generated a community. And sometimes we overlook that, the value of the community in our subdisciplines, and we can still see a lot of evidence of this community in work that we do today. So there was a lot of vision from Susan and others there to get this going. Early on, we really focused on using geophysics to look at aquifer characterization. Here's a study from some work that we did a long time back on ground penetrating radar between boreholes, looking at variation in moisture content in the unsaturated zone of the sandstone aquifer. We kind of focused on looking at structures there in these detailed plot studies, and this has evolved now to more comprehensive studies that bring together multiple data sets. Here, an example from Susan Hubbard's work using Bayesian techniques to come up with characteristics of the subsurface that will help you understand reactive transport processes. So the whole thing is kind of evolved now to using multiple modalities and multiple data and bringing those together in a stochastic framework. We've spent a lot of time in the community looking at relationships between things like permeability and geophysical measurements. Here's some examples looking at induced polarization, links to permeability. And you know, sometimes maybe we're just doing a little bit too much navel gazing here, and we kind of get obsessed by looking at these relationships, and maybe we need to think about just using the trends, spatial and temporal trends, in these proxies, rather than actually being obsessed by trying to get a universal relationship to permeability, for example. We can take advantage of new measurement techniques, development of instruments. Here's an example using multi-coil electromagnetic sensing. It's a riparian wetland here. Here are some measured peat thicknesses on this chalk aquifer in a riparian wetland, and here's our geophysically derived model of this system. And we can see we can get a fantastic spatial resolution of these properties, and this is really going to be useful for looking at the links between the aquifer, the wetland, and the river system. And we can also move into river corridors. There's a lot of work that's been done on this, and my colleague Adam to my right here has actually done a lot of work in looking at geophysics in the hyporheic zone. I just want to highlight one example. I'm biased, so I'm going to highlight my own. And this is from a small river reach here, using simple technique, again, EM, waterborne EM measurements. And here we're looking at variations of pore water in the riverbed. And the reason is that we're trying to identify areas of significant upwelling of a regional groundwater because it has a different geochemical signature. And we're interested in that because of a legacy nitrate problem. And we tried temperature in this case, and we couldn't really get a good temperature signal because it's such a diffuse source. But it's localized, but it's actually is significant. And so we might actually want to think about actually not trying to map an entire catchment when we're looking at working in catchments. We might want to think about measuring along stream networks, and we can get a lot of useful spatial information that might allow us to target more detailed plot studies. There's a lot of work that's been done linking hydrological models and geophysical data, and here's some kind of early work of ours looking at a one-parameter model here. So we're trying to calibrate a one-parameter Richards equation. It's less than 10 meters, so John, well, I think we're okay with this. And so we're trying to calibrate a Richards equation model here to look at the movement of a solute plume that we've injected in this small plot experiment. This is kind of really simple, but it shows how we can use the geophysics. And then this is some work from Tim Johnson using a more sophisticated linkage between geophysics and a hydrological model to get now permeability variation. So things have advanced quite a lot in linking hydrological models and geophysical data. I don't think we actually do enough of that. And actually, I don't think we do enough of actually using hydrological models to design our geophysical surveys. We kind of, sometimes they kind of they're treated pretty separately. There's a lot of interest in geophysics now to working with agriculture. We saw some examples earlier with remote sensing. At a plot scale, here we've been using some geoelectric surveys to look at whether we can use these techniques for phenotyping. Plant breeders kind of want to know about where the roots are taking water from. So we've been running experiments to see whether we can actually use these as some kind of phenotyping solution, in this case for winter wheat. And from Sander Hoosman at ULIC, presentation yesterday, which kind of shows how in using EM surveys, electromagnetic conductivity surveys along a field plot, getting information about soil texture variation and feeding that through with other data to get an idea on productivity within there. And there's a lot of interest I know now, certainly in the UK, in agriculture, in actually combining some of these geophysical techniques to enhance yield. In some cases, geophysics has been used to test hypotheses, and here's a nice example from two casual-looking colleagues here, Lee Slater and Xavier Comas, in a peat bog. And basically what they wanted to do was actually see whether they could see evidence of methane in the peat and where it varies. So this kind of illustrates nicely from ground-penetrating radar a map of effectively gas content, and the gas content highlights here in these woody, shrubby areas, they say elevated methane, whereas in the lawn area, there's reduced amounts. So this can kind of feed into peatland carbon cycling models really effectively. And here's another example from Susan Hubbard's work, which kind of along the same theme, but now looking at a permafrost environment, and not trying to use the geophysics to come up with a detailed characterization locally, but trying to use the multiple geophysical methods to actually identify zones, different functioning zones within the area. So actually, I think this is a really nice example of how you bring a whole lot of data together, and actually you come up with a relatively simple representation of this complex problem that allows you to kind of target areas of investigation or look at changes over time. There's been a lot of developments in inverse methods in hydrogeophysics, and some of these are actually using stochastic techniques, and they kind of then implicitly deliver an assessment of the uncertainty, but we don't really use that much. We don't really present that. And if you work with geophysics a lot, you kind of know what the right glasses to wear to kind of interpret things, but I think sometimes when we transfer that information to other people, we need to be a little bit more careful in communicating our uncertainties and showing uncertainties. And I think in the hydrological community, that's kind of accepted, but it's somehow in the near surface geophysics community, it's less of the norm. We also need to think about these links, these petrophysical relationships that we have. They are also uncertain, and in many cases, when we want to quantify information from our geophysical data, we might rely on literature values of relationships. And if you actually delve into this, as we've done here, and start measuring multiple relationships on multiple samples, we see a lot of variability. We need to think about how that variability propagates through in our estimates. So there's a lot of uncertainty there, which I don't think that we're actually projecting or even quantifying. In terms of technological developments, there's a lot now automated systems out there. They're widely available, and here's an example from the British Geological Survey, their PRIME system, which is a low-power geoelectric system. Here, monitoring moisture content changes on a railway embankment in the UK, looking at moisture content changes to look at the vulnerability here in this local plot. So some of these systems they're automated, but some of them also offer some kind of autonomous self-learning solution. And I think there's going to be a lot of further advances there, particularly when we think about these low-power systems. A lot of advances in mobile techniques, waterborne and ground-based techniques for surveying areas, and if you live in Denmark or in the Netherlands where it's pretty flat, then maybe you're okay with these kind of things. But there's a lot of effectiveness of these mobile platforms for geophysical surveys over large areas. Airborne surveys in hydrogeophysics have advanced recently too. I mean, these techniques originated for a lot of resource evaluation, but they're now becoming integrated into a lot of hydrological studies. And this is a study that I thought was awesome, because this came out of GEOS in Copenhagen. And what it does is it brings together airborne EM data and actually looks at, this is the horizontal slice 50 meters above sea level through their geological model as an example. And it basically shows how you can use the borehole data and geophysical data to improve your characterization of those units. And then you can imagine feeding that into a model that then you use for predictive purposes. And this is, in this case, working with transitional probabilities, so using your airborne and your borehole data to come up with some map like this. There's also developments in other airborne modalities. Here's an example of something that's recently come out of ETH Zurich from Hans-Rudi Maurer. This is a glaciology study looking at ice thickness here, but I just wanted to highlight this to show you that kind of some crazy people are flying helicopters with the GPR antenna on there now, and there's possibly scope in some other areas for these kind of applications. And obviously, it goes without saying that there's also interest in some drone UAV type technologies as well, and there's no doubt going to be a lot of advances in the future. Maybe they're going to have limited applications, but there is definitely scope there. So just to wrap up here, I think just a few points. We've done a lot of plot experiments. They're good for demonstrators, but we always need to think about generalizing. How do we actually generalize information? I spent a lot of time working in one plot in the UK, and the environment regulators, they actually wanted to know about the entire aquifer, not that one plot. So we need to think about generalization. We can't map everything, but maybe if we look at hinge points in the system, and I use an example here, this conductivity mapping within a river corridor. Inverse modeling, I think we need to do more with uncertainty, demonstrate it, and actually think about where it comes from. And I think we can do more by integrating hydrological models in our geophysical studies, not only with the inversions, but actually also thinking about survey design and what our particular problem is and how we might actually design the geophysical survey to do that. And the final point here, I think in some areas we might want to branch out into more areas of greater societal impact. I'm as guilty as any of actually focusing on some things that maybe, if I spoke to the layperson, they kind of couldn't see the relevance of that. But sometimes we might need to think about simpler technological solutions, not the most complex solution, to tackle some problems which are real challenging problems out there. And I'm going to finish there. Thank you.
We're going to have to hold questions.
Okay.
Okay. So our next speaker is Mike Gusev, talking about surface water and groundwater interactions.
Stairs, I think. Great, thank you. Thanks for coming. So I really wanted to call this 82 years of groundwater surface water interactions. I have a colleague who convinced me I could go to 150, so I'll explain why in a moment. But I arranged this talk around what I consider to be the primary literature for where we are today with our conceptual understanding and sort of an outgrowth of sort of our current state of the art of understanding stream groundwater interactions. So with that, I will note that I am not going to go into runoff generation, coastal aquifers, lake groundwater interactions, wetland groundwater. There are a lot of great advances there. I'm going to focus on mostly streams here. And I couldn't cite everyone, so my apologies in advance if your really important paper is not included here. But some of these are pretty old. So you can argue with me after this if you'd like. Okay, so Aaron Packman convinced me that 82 years is really lame. Why don't you go back 150 years, because we can include Darcy, who brought groundwater to these fountains. And I guess I'm trying to convince you of that. I'm not really sold, but 1856 seems like a reasonable place to start for thinking about groundwater surface water interactions. These are not the ones that we'll talk about for the rest of the time, but I think it's not a bad benchmark to start with. However, in 1936, Troxel from the U.S. Geological Survey noted that in the Santa Ana River in California, over on the right side here, these are a little hard to see. This is from EOS back in 36. These are data from 1932, and what he demonstrates here is that the sort of daily sinusoid of changes in groundwater elevation were following those in the river, which was the first notion that these two things were synchronous in some way without a direct sort of application or trying to figure out whether there was a direct linkage of exchange, but noting that there was this boundary condition to the two of them sort of working in concert. However, it was not until 1959 when we got to over to Europe to note that, I've never said this before, but Ogadan basically went through and noted that when he was digging around in these Romanian streams in Europe, throughout Romania, pardon me, he found a bunch of macroinvertebrates. And at depth, these macroinvertebrates were not just at the surface, but if you dug down within a meter of the surface of the stream, what is going on? Why are these bugs down here? And so eventually that got us to start thinking about how the conditions in the subsurface of these streams must be similar to what's going on at the surface. And so he started to call this the hyporheic biotope, that's about as much data, by the way, as is in this paper, unfortunately. But that a lot of work built off of this from Dudley Williams in Canada, Jack Stanford, and so forth, sort of trying to understand what was going on in the beds of these rivers. Walter Vo, on the other hand, was working as a chemical engineer here in Alaska, noting that salmon redds were being built in places that really depended on stream groundwater interaction, and he focused on these gravel bed rivers in Alaska. In fact, he even went so far as to sort of build some little BAF models to develop his numerical model, which we all, I think, take a little bit for granted now. But he also went so far as to say, if we wanted to increase the exchange through the bed and have more salmon or better habitat, we might actually go and engineer these channel beds to have low permeability and high permeability sections to drive exchange. And so the notion in 1968 even of stream restoration for habitat perhaps was born. I don't know of one earlier than that. When we get to Jack Stanford's work, though, in 1974 and 1988, these were some pretty big papers that came out in Science and Nature. Jack went out into some of these big alluvial rivers in Montana and pumped the heck out of at depth and found macroinvertebrates being pulled into the water that he pumped from. And so noting particularly in the Flathead River, the channel is about 50 meters wide. It might be 1 or 2 meters deep, but the hyporheic zone was as much as 3 kilometers wide and 10 meters deep. So the volume of this interstitial area that would be exchanging water between the surface and the subsurface was quite large and providing habitat for macroinvertebrates. So the standing crop of biomass in the hyporheic zone could easily exceed the biomass in this river in this case. As we move forward into the early 80s, perhaps one of the more seminal papers is this notion of bringing the Otis model or the transient storage model here from Ken Benkala's work in the early 80s. Ken went out and not only sort of brought this solute transport model together where we have advection, dispersion, some lateral exchange or inflow of water, and then this exchange of water between the main flowing channel and some dead zones or transient storage zones. But he also then in that paper sort of demonstrated that if we just use advection and dispersion, we don't fit the data very well from a tracer experiment conducted in Uvis Creek. And if we include storage, we get a much better fit to this data, right? So this was sort of the beginning of lots of different types of solute transport models. We started to maybe tear those apart in different ways, come up with different residence time distributions, et cetera, to try to explain this retardation of the signal and this late time behavior. And eventually we got to the point of starting to think about the chemical impacts of that. And really Ken's work was focused, he told me once, that the transient storage model was built for explaining stream chemistry, not physics. And yet so many of us, I think in part because a lot of ecologists were running to this as well, sort of wanted to try to explain some of the physics or the exchange of water between the channel and the subsurface with these types of models. In 87, this was the earliest I could find of this is, so Nature in 1987 isn't the journal it is now, but here is a picture, black and white picture of a dune in a flume and putting dye into the bed to look at where it moved and basically identifying these exchange patterns through bed forms. And so the hydrodynamics was starting to catch up now a little bit with the notions that had come to us from not only the biology and habitat that was out there, but also this notion of moving water that was exchanging between the stream and the bed in some way. And so this paper by Thibodeau and Boyle then goes into sort of these classic triangular bed forms and thinking about their similarity to a very simple model down here of flow moving around these circular sort of projections. But in any event, this really spurned a lot of work that Sandy Elliott did and Aaron Packman and Bionic Cardenas today. There's a lot of great work that came out of that sort of, I don't want to use, it built on this, even though we might call it derivative, but I don't mean that in a negative sense at all. I think we've come a long way in understanding and being able to predict what happens is with residence times and biogeochemical processes in systems like that. However, that doesn't necessarily apply very well to gravel bed streams that we see in some headwaters. And so when we go back to California now, this is some work, Frank Triska's set of 2 papers that came out in Ecology in 1989, really defined for us these biogeochemical gradients that they had seen in a number of places, but certainly were highlighted in Utivas Creek, where we see high DOC at depth and low DOC at the surface in the stream beds, and then really tried to define a surface zone, an interactive zone, a groundwater zone, and then noting this notion of hyporeic zone. So coming back from the hyporeic biotope that Ogadin defined for us, Frank was the first one, I think this paper was the first one to really try to define from a hydrologic perspective that this was a mixing zone and that we must have somewhere between 10 and 98% of surface water in the subsurface. So we do this with some sort of mixing model in some way, trying to identify the mixing of 2 end members. But this was, I think a landmark step forward in trying to understand, okay, now how do we get water in between, and what does it mean to have sort of those relationships? Now, so Frank further worked with Brian Kim, I believe was a student of Frank's, working with Frank and Alan Jackman. And one of the things that Brian did is he went further to, they did a nitrate injection experiment here. And what you see is that if you go without storage, the best fit you get to the data shows that you're way off from the nitrate injected data here, the data points. If you include exchange without uptake, you get a poor fit again. And if you include exchange with uptake, you get a much better fit to the data. So this was demonstrating that somewhere in the storage zone there was uptake going on, in this case of something biogeochemically relevant, something relevant to water quality. And when they run this experiment for 7 days, you can see that they basically had variable uptake. V max is just an uptake parameter here for nitrate in the stream, and basically varying from 0.12 to 0.25 micrograms of nitrogen per second per gram of ash-free dry mass in the channel. Moving forward into the 90s, we really started to get into more of the architecture of small streams. This is work from St. Kevin Gulch in Colorado, where there was some nasty acid mine drainage systems. But Judd Harvey came out as a postdoc and really spent a lot of time trying to understand what was going on from a mechanical perspective to move water between the channel and the subsurface. And what isn't included in this is a profile of the water surface, and what's not included there is a profile of the bed. But essentially, Judd was identifying that this upwelling and downwelling sequence that we see in the lower part of this image is really water moving through kind of in accordance with these slope breaks at the surface. And if we, but it wasn't just a vertical perspective. He also had this lateral perspective of trying to understand how hill slope flow was coming down and interacting with the channel, and basically there were these bypass flow paths around some of these transitions between riffles and pools. In the same year, Ken Benkala wrote this really nice little perspective paper in JNABS. It was part of a series on hyporeic studies that really went to identify, the stream streams are not pipes. They are an essential part of complex watersheds, and they do a lot of processing as water moves down them and out of watersheds altogether. In 98, we jumped forward a little bit. There had been a lot of work done in the desert Southwest by Nancy Grimm, Cliff Dahm, and several others, Maury Villette. And this was a really nice paper, just to try to summarize a little bit of this from Cliff Dahm and several others, indicating that rivers themselves can drive a lot of what we call nutrient cycling, the uptake and release of nutrients along a flow path. But they can also, the river corridors, the riparian zones, provide a lot of buffer capacity for flow paths that come into channels. And so this paper isn't very widely cited necessarily, but I think there's a really nice context of thinking about sort of gaining, losing, and parallel flow path streams and how much nutrient processing can occur, or in this case they called it nutrient retention efficiency. So this remains a really nice set of hypotheses to go and test in a number of systems. But then in 98, I think the title of this circular from the USGS really says it all, that groundwater and surface water, a single resource, really demonstrated the maturity of our understanding that these things were connected, that when you affect one, you affect the other. It may not be immediate, but certainly they are connected, and it's a really nice summary. These are some of the classic figures that come out of that work. I'm clearly running out of time, but this was a maturing of our understanding and moving beyond. I think in 2000, Bill Wussner hit us over the head and said, hey, groundwater hydrologists, there's all these cool things going on in small valleys with streams, and why don't we start to think about the complexities of this system and what this means to us. Moving forward a little bit, jumping through the 2000s, I realize I'm skipping over an awful lot, but this is one of the only papers that I've cited of my own work. But Adam's work here, and building on what Andrew just talked about a little bit in the context of thinking about using geophysics, in this case resistivity, to look at changes or the movement of salt-laden water into the subsurface and trying to identify where the true extent of the hyporheic zone is, has really allowed us to start seeing the things that we've only drawn cartoons about in the past. And Jay Zarnetsky built on this with a lot of understanding of complex biogeochemistry along flow paths through, in this case, just a very simple bar, but it's really opened our eyes to understanding the sort of the predictions that we can make about the consumption of oxygen and carbon when nitrogen is getting cycled in these flow paths. Coming to sort of more immediate findings, this was a paper that Judd really led. I mean, he and I are on this paper, but this was really Judd's brainchild of this river corridor concept, where we start to put the river corridor in context and think a little bit about how we can try to predict time and space scales that are important to the processes that we care about, particularly when it comes to maybe habitat exchange or understanding of particular processes that are important for water quality. So here's a little timeline of what I've just showed you, but I want to note then, or put this together, that this ecological curiosity has led to an understanding of facilitating sort of pollutant removal from stream groundwater interactions, eventually to, that's hard to read, essential to healthy ecosystems, understanding this true underpinning to the river corridor concept. And ultimately, I think that we face a challenge. That when I landed last night at Dulles, one of the first emails I had was this news alert from the New York Times indicating that, the current administration wants to change the Clean Water Act. And the Clean Water Act in the US originally said that the goal is to restore and maintain chemical, physical, and biological integrity of nations' waters. So much of these exchanges are really invisible. They happen under our feet. They're not obvious. And I think one of the challenges that we face then is to really try to get people to understand what these do, how important they are to underpinning the ecosystem services that we all face and the challenges that we face in trying to manage rivers for water quality. So I'll end with that. Thank you.
Thanks. We're going to hold questions to the break. Our next speaker is Stephen Lohide, and he's going to talk about groundwater.
Okay, well, I want to thank our conveners for giving us this opportunity to reflect on the evolution of our subdisciplines over the last 100 years. And I'm excited to be able to talk about groundwater in this regard, but I want to start with just a caveat that given 9 seconds per year, I'm going to skip over some of the finer points. So what I really want to focus on is what has changed in how we approach groundwater science here at AGU. And so I want to start by painting a picture of what an AGU meeting looked like in the early years. And you can get a good idea of this from reading the transactions of the American Geophysical Union, shown here for the 20s, 30s, and 40s. Then I'm going to give a broad stroke timeline of the major contributions in groundwater science, and then use the technical program from this year's abstracts to provide a sketch of the diversity and scope of groundwater science today. Here's a little bit more clear indication than just the stack of the books, showing the increase in the number of abstracts on groundwater as one word or two, or the unfortunate term underground water, which was preferred at the beginning of the last century. One of the hard things to really put my head around was AGU was a small organization. It was capped at 75 members for most of the 20s. They increased that to 100. The first, third, and fifth meetings were devoted to discussion. There were no research papers presented, and we lacked a hydrology section at that time. So for the first 10 years, there was really very little about groundwater. Here were the 7 presentations at the first meeting. They were by the section chairs. It also occurred in DC, just a few blocks away from here. And then there was one during the period 1920 to 29, one session that related to groundwater, some work from Mainzer, and a report back on this symposium on hot springs. And what I want to make, the point I want to make with this, is that they talked about the areas where there was general agreement from the 10 speakers, areas where there was disagreement, and whose data sets supported each side of the argument. 1930, we finally get a hydrology section thanks to Dr. Littlehales, who was actually an oceanographer, but at the meeting the following year, talked about the inception and development of the international section of hydrology. At this meeting, there were also two other big picture what is hydrology talks. One was by Robert Horton, showing the hydrologic cycle here. Maybe this was the first one that David Hanna had in his hydrologic cycles. There was another description of the field of hydrology by Meinzer. This year, there were two papers on groundwater. The first one here was a field experiment. A hole was dug, an intercepting pan was put in place, and the purpose was to investigate the absorption and precipitation of water and its penetration to the zone of saturation. What I love about this experiment is that it was a failed experiment. No appreciable amount of water was collected. The method was abandoned and the problem attacked by other means. Who's presenting a failed experiment this year? I think that might be a sad thing. They learned some things from this experiment, and in fact, they kind of learned that it was functioning like an uncracked Yucca Mountain, and the capillary forces in the soil were causing the water to circumvent this intercepting pan. In 1932, the Technical Committee for Groundwater was fully established, and they provided a report, a committee report, on underground water. It was chaired by David Thompson, and they had to define the scope. And they said Meinzer, the year before, had listed 26 areas of hydrology. Well, us in groundwater, let's take half of them. And so those are the areas covered by the committee. And then the committee members all got together and talked about all the recent and current investigations that they were aware of, and they documented them. They talked about what the USGS was doing, collecting not only statistical facts, but doing fundamental science. They talked about papers by Meinzer that had been published that year. They talked about who was collecting data in different parts of the country. They talked about individual studies, this professor at Harvard studying porosity and permeability, and they talked about what state agencies were doing around the country. And they compiled all this information. They also solicited suggestions on what desirable lines of future research were for the committee. So this was a committee report in 1932. There were also 5 papers on groundwater. This was a pumping test conducted over 48 hours. 12 men ran around to these 80 wells and collected water level measurements around the clock. And at the time of publication, the data had been partially interpreted. Tice presented flow lines to a single well. 2 investigations showed water level fluctuations in Pennsylvania and Virginia, and interpreted when recharge occurred. And then a final presentation was on interactions between groundwater and the oil industry. That was the meeting in 1932 as it related to groundwater. So now let's see where that path took us and look at the contributions. So I'm going to take and look at these benchmark papers that were compiled by my friend and colleague, Mary Anderson. And she divided those contributions into 7 different areas, starting from the beginning when we were establishing and developing our groundwater resources for municipal use and for agriculture. And people had to know how aquifers worked. They were interested in the poroelastic effects and subsidence that they were seeing occurring. This then led us to a need to parameterize and understand the properties of our aquifers better. So we developed pumping and slug tests. We then, as a field, kind of got beyond our obsession with single wells and looked at larger scale flow systems, which naturally led us down gradient to looking at discharge points and looking at interactions with surface water. As our models became more complex, we became more concerned, and still are, with parameter uncertainty. And then with the passage of the Clean Water Act in the 1970s, a good portion of our community shifted to working on contaminant processes. And as we failed to explain the long tails of contaminant transport, we started looking at dispersion and heterogeneity. And that brings us up really to the modern era. And now we look at AGU, and it's a whole other beast entirely. We now have more than 62,000 members from 137 countries, so a very diverse group. Recent annual attendance at this meeting has been about 24,000. I think we're several thousand above that. 25,000 abstracts. The hydrology section alone had 3,253. And when I searched abstracts with groundwater, there were 1,150. So this is made possible by the community getting together and developing these, the hydrologic section, and the groundwater technical committee, which itself is a diverse group with diverse interests, research interests related to groundwater from all across the country and the world. So I looked at those 1,150 presentations that are being presented this week, and I sorted them into different themes. I picked out only 6 themes here that I'm going to talk about, just very briefly, and one of them relates to sustainability and interactions between groundwater and crops, both for extraction and direct use by the plants. We look at kind of the full food, energy, water nexus, and people are investigating groundwater energy problems, including the effects of shale gas development on water quality, as an example. We are getting on the wagon with big data. We have more data than we've ever had before, and we're using big data and machine learning approaches for a whole wide variety of applications. Our sensors of all kinds have come a long way. One portion of those are the remote sensing, the ability to measure gravity anomalies and associate those with changes in water storage on the planet is pretty amazing. Our models, we followed the blueprint by Al Fries and have integrated surface water and groundwater modeling and are now able to perform that at continental scales. We're also engaging in social hydrology and understanding the coupled human and natural systems and how decision-making processes occur. So when I look back at what's changed, I think that a lot has changed. The early meetings were really small, and participants came away with a common experience, a single meeting experience. They had painstaking efforts focused on documenting all areas of research that they knew about across the country, and synthesizing those results, as well as identifying areas where there was agreement and consensus, and areas where there was disagreement, as well as opportunities for future work. Throughout history, groundwater has been an applied science, and I think we can take a lot of pride in our responsiveness to societal needs. We look at AGU now, and it's enormous and diverse and fantastic. And if we think about what our predecessors wouldn't have been able to imagine, it's almost everything. In over 100 years, I guess that's not surprising, but we have a lot of new tools. We have a lot of new methods, new models, new problems, some of our own making, and new connections to sister disciplines. So I feel like when I come to AGU, it's like drinking from the fountain of knowledge. But it's also a little like drinking from the fire hose. And so what I want to think about is, as a takeaway message, I think we've really changed the way we digest scientific information. And a lot of that, I think, is really valuable, right? We've shifted AGU in ways that have enabled extraordinary advancements and have accommodated this explosive growth, right? But I want us to also think about, as a community, is there a way that we can be more mindful in our synthesis and reflection on this event, even though each and every one of us has a unique experience. We have a unique set of talks that we go to, and unique takeaway messages. And so I'm going to leave it there, and I welcome any comments that you might have.
We have time for questions.
Yes.
Well, given the change in technology, we can now document things, search things, and present things in whole new ways. Yet, so many times we see people giving talks and they're lost in space. How do we correctly address the technological opportunity to deal with the volume and diversity of exploration?
I think that's a fair question, right? There's so many activities going on. Are we aware of them, and are we taking advantage of it? That's a community question.
Right, thank you, Steve.
Okay, our last speaker of the session is Matthew Cohen. He's going to be talking about water quality.
Well, good afternoon, everybody. Thank you to Adam Ward for the invitation to speak to you today about water quality. I'm the current chair of the technical committee in water quality, and so that seemed apropos. Although I did note that he waited to ask me until we were several beers into the evening. I'd also like to do a shout out to Kwasi. The last three speakers, myself included, are on the board of directors of Kwasi, and I think that's an important synergy between AGU and other groups trying to forward the hydrologic sciences community. So my task was to take a centennial view of water quality. I'll acknowledge that a lot of the conversation that I'll relay here was informed by discussions with Jim Jowetts, and so I've elevated him to a co-author, maybe to his peril. So I want to start, if you know me, I usually have too many slides, so I'll start by taking you to the three main points that I'm planning to relay, and that is that perhaps as no surprise, what we mean by water quality, the things that we've attended to in terms of remedial actions has evolved, and this is an ongoing process. The things that we refer to as emerging contaminants today will in 50 years be hopefully well dealt with, and we'll have a new suite of problems to deal with. Contemporary water quality, as we measure it in a stream or an aquifer today, is a long integral. And the long tails that Steve spoke about in terms of the transport through the landscape frustrates our remediation, and that's something that as water quality experts we need to get a handle on. And that the remedial costs are large, and there is an important role for water quality specialists to play in enumerating the benefits, because I think the alternative narrative that the costs outweigh the benefits is out there. So to start with, we have shifting baselines. Back in the 1850s along the Thames River, monster soup of the Thames River, these were massive open sewers discharging into the river during the summer of 1858. It was so bad that this quote, gentility of speech is at an end, it stinks. This was so bad, in fact, that Parliament allegedly moved their discussions away from the river because the smell was so offensive. And of course, it wasn't until Parliament found the smell offensive that there was action taken. Meanwhile, in the decades up to that, there were massive typhoid outbreaks, 10,000 people dying in an individual summer in the early 1850s. Fast forward to the 1930s, starting in the 1930s and continuing into the 1960s, we have this iconic story of the Cuyahoga River running through downtown Cleveland with this veneer of oily, slick material from industrial discharge. And this is a picture from 1952, the best picture that they were able to find. This is a Time magazine archive showing the river on fire, which I think the public rightly identified as a problem. And that was, at least in the common narrative, the impetus for the Clean Water Act and coming to our senses about our need to maintain water quality. More recently and closer to home for me is the changes in the nutrient concentrations and the changes in the temperature regime and flow regimes that are leading to fish kills like this in the coastal zone of southwest and southeast Florida, and that this has been a burgeoning problem. And so that is a very different set of scenarios. People dying and being exposed to typhoid, to fish kills is a different suite of problems. And so I think it's important to sort of motivate the conversation about water quality by thinking about risk. And Peter Sandman's paper in 1993 sort of divides risk into a hazard part. That's the part that we as scientists are obliged to try to populate. That is to say, objective technical aspects of risk. How likely are various negative outcomes? And along this axis is the sort of the spin room, if you will. This is the outrage, and it's the extent to which the population is upset, frightened, or angry. And of course, those things are not necessarily correlated. When they are correlated, we have the appropriate responses to problems. Frequently, and I would argue that AGU has been instrumental in trying to elevate the risks of global climate change into the national discourse, as many of us have, but that the public is inappropriately fearful of the consequences. And then, of course, there are times when there is outrage, but that the actual technical hazard is relatively low. And I think this is a useful framework for thinking about how we respond to water quality problems. So a classic paper from 1989, Mabeck and Helmer, was basically trying to understand what has been the trajectory of water quality. And of course, those shifting definitions means that what we define as water quality is not always the same thing. Of course, we started off with, is there typhoid bacteria in the water? And that's an important concern and probably your primary concern. And you're not so worried about whether there's a fish kill or whether the estuary is eutrophic. But as we've solved that problem, new problems, salinization, metal pollution, eutrophication, now here's nitrate, organic pollutants, acid rain, this thing ends in the 1980s, and you can essentially fast forward to a whole suite of contaminants that are now in the news. We'll come to those in a moment. Essentially moving down Maslow's hierarchy of needs, starting with our safety and ending with our desire for a well-curated, safe, and sustainable environment. And so that's an important part of the story in water quality that I think will sort of stay as a theme for this talk. One of the consequences of that is that each time we identify a new constituent of concern in the water quality arena that is impacting our environment or generating outrage, we basically add to the list of things that we measure. Right? And so starting off with dissolved oxygen in E. coli, and as we've identified new and emerging contaminants, that list of things we measure has expanded. And anybody who tracks the EPA STORAT database, there's 35,000 or more analytes that are measured. It's a comprehensive and almost bewildering enterprise of various ways in which water quality can be impaired. And so each emerging priority adds analytes, but it doesn't actually get rid of any of the previous ones. And so we have a sort of exponentially growing constellation of things that we're measuring. So one way to think about this is a paper from Sam Arden and Jim Jowitz. It's in review, sort of recasting Maslow's hierarchy of needs from things like, are people dying, to the provision of ecosystem services and sustainability and beyond. And these are data assembled from Cincinnati wastewater treatment. Starting off with just basic wastewater treatment, you can see the decline in typhoid incidence per 100,000 with the association of the installation of sort of basic wastewater treatment, filtration, and chlorination. One of the things, so this over here is essentially the investment, the energy investment in the enterprise of collecting and treating wastewater prior to discharging it to the Ohio River. Here's the transition to putting people on central sewers. Here's addressing BOD. Here's trying to reduce to total organic carbon. Here's looking more at nutrients and the attainment, if you will, of biological criteria. And each time we do that, we increase our social investment in protecting the water resources, and there are attendant benefits that go with that. And that balance of the costs and benefits, I think, is an enormously important part of the conversation that we'll come back to in a moment. Mabeck and Helmer also proposed that there was essentially, many of you will have heard of the demographic transition. The water quality transition essentially starts with the situation where there's no problem because the intensity of the human enterprise isn't there. But as the human footprint increases, water quality issues emerge, and in the absence of controls, those essentially run away. But in most cases, what we see is societies adapt and respond in a way to try to remedy those controls. So here's an example. This is, again, typhoid. You can see the declines in all major North American cities in typhoid incidents with the advent of modern sewer systems and even basic water treatment. Between the 1930s and 1936, it was engineers that were responsible for the most important public health changes that occurred in the country, something on the order of 3/4 reduction in infant mortality. And just to sort of put a diagram on this, this is the incidence of typhoid in books as summarized by Google by decade. And you can see in 1900, 1910, there was a peak. People were really worried about this. They were outraged about typhoid, rightly so, because people were getting sick. By the modern era, typhoid doesn't really come up very much. When you hear about it, it's usually in places like Haiti where we are outraged it's happening there. But it's not as the incidence is much lower. Here's another example of this water quality transitions for trichloroethylene. So this is basically the combined sales as we started to realize that the water was contaminated. It started in 1949 with a report suggesting that there was TCE detected in groundwater. By the mid-1960s, the problem had reached the point of outrage where the water in New Orleans tasted oily, and it was by the 1980s that we saw the President's Council on Environmental Quality conclude that millions of people rather, were affected, and that was the sort of commensurate response. So we have a sort of time scale of social detection of the problem to hopefully the remedy of that problem, at least with regard to the human health consequences, of 30 to 40 years. This is actually a quote right out of Silent Spring, one of the iconic environmental documents of our age, saying that in the entire water pollution problem, there's probably nothing more disturbing than the threat of widespread contamination of groundwater, just to animate what Steve was talking about just a moment ago. As we think about the emerging contaminants in the modern era, we think about things that are endocrine-mimicking endocrine-mimicking compounds. This is a study from a lake in Florida, Lake Apopka, where they found that mature alligators had very small penises because of low testosterone. Nothing generates outrage like headlines like that. Equally, a recent report in Nature Communications where they found that downstream of a wastewater treatment plant, because of food web accumulation of things like antidepressants, platypus, consuming riparian spiders in that system were actually being exposed to about a 50% of a human dose on a mass per mass basis. And so those are emerging contaminants that are generating alarm in the public. I think our job as water quality experts is try to characterize the hazard. But these are the things that we're going to be contending with for the next 20 to 50 years if we think about the water quality transition. Microplastics is something that everybody has heard a lot about. I was really struck by this graph that even over the last 20 years, there's been a tripling of plastic loads. I thought of plastics as something that's been around longer, but this microplastics issue is emerging as something that is very much on the minds of people who are worried about marine pollution, about even freshwater contamination. So this is one of the new challenges. A second theme that I think is important, particularly when we think about remediating some of these problems, is that the landscape has an enormous capacity to store the contaminants that are being exported. And so when we're thinking about water quality in a place like the Thames, here's a very long data record from Nick Howden's work showing the nitrate concentrations in the Thames since the mid-1860s. And you can see that in spite of what is quite evident decline in load, maybe it's modest, but it's certainly happening, the nitrate has been quite resistant to declines. And moreover, they argue in their paper that this peak right here, which was food production in service of trying to win World War II, actually has had this durable effect of creating a persistent nitrate problem in the landscape 50 years on. That was reinforced by work that Kim Van Meter and Nandita Basu and Philip Capellan published in 2018. This is a graph out of that suggesting that the nitrogen loading to the Gulf of Mexico from the Mississippi Basin, if we do nothing, we're already on a downward trajectory of nitrogen use. BMPs, various agricultural efficiencies are already making a difference. But if we want to get back to this background concentration that is the target load, and we decrease our nitrogen inputs by an astronomical 25%, that would be a big change in the landscapes of most of North America. We probably are within the error bars of being able to detect that by 2050. And then if we want to get down there by 2050, that's now 32 years away, we would have to essentially eliminate nitrogen fertilizer to the landscape. These are vexing long-term problems, and they don't they create a lot of anxiety amongst the public when payments to do things like implement BMPs are not translated into rapid results. This is what recovery looks like. This is a nitrogen loading in Tampa Bay. One of the consequences over that 30-year record is that as the nitrogen loading has declined, chlorophyll A levels have gone down, and we see the seagrass beds recovering. Likewise, we have this maddeningly slow recovery of phosphorus loads in Lake Okeechobee, or nitrogen loads in the springs in Florida. I want to close with this. It's important if you can hang out from lunch for just 1 minute. There was a paper in 2018 that was indicating that the investments in water quality controls somewhere on the order of $2 trillion since 1960, $140 per person, which I think everybody in this room is more than willing to pay. But justifying the costs of that are actually pretty important for policymaking. And when the Office of Management and Budget has gone through and evaluated the benefits of these water quality programs, the average benefit to cost ratio is substantially less than 1. Right? So in spite of this enormous investment in water quality protections, the federal government is of the opinion, potentially, that these programs are actually not worth it. There's a lot in this paper to suggest that that is an erroneous inference, that in fact we dramatically underestimate the benefits of water quality programs. The most striking example of that underestimate is the example that Mike Gusef referred to, which is as of right now, today, the EPA is unveiling plans to, I wouldn't call it rework, I would call it roll back clean water protections under the Clean Water Rule. The reason that they're justifying this in their internal documents is that the benefits of water quality, when that law was signed into effect in 2015, those benefits were positive. The benefit to cost ratio was positive. But they subsequently said, well, there are no reliable benefits of protecting wetlands, and so consequently the benefit to cost ratio became basically zero, and that is being used as one of the internal justifications for this. And that is a signal that we are not standardizing our understanding or our representation of the benefits of water quality protections. I think that is an important challenge for us as a community. So some challenges, more or less what I just said. We need to continue to attend to old and new water quality contaminants. We need to tune our policy and regulations to represent these recovery timescales, and we need to do a much better job of articulating the benefits. So with that, enjoy your lunch.
Thanks to everyone for coming, and thanks to our speakers. And Matt will stick around if there's any questions folks want to grab him for.